point to start is an introduction. So could you please introduce yourself and talk a little bit about your background?
Okay, so it's nice to be here. I'm Roman Orus. I'm the scientific director of Multiverse Computing, and I'm also an Ikerbasque research professor at the Donostia International Physics Center in Spain, the DIPC. You know, I'm a physicist. I did my PhD back in 2006 on quantum computing at the University of Barcelona. Then I've been working in many places. I worked for a while at the University of Queensland in Australia as at the group of Guifre Vidal. Then I also worked at the Max Planck Institute in Garching with Ignacio Cirac for a couple of years. I was a professor of condensed matter physics a junior professor of condensed matter physics in the University of Mainz in Germany. Then I came back to Spain as a research professor. And then in parallel to all this, I founded together with 3 other people Multiverse Computing, which is one of the leading companies in developing quantum software for worldwide and in particular for finance.
Yeah, and could you talk a bit about how you combine quantum and finances? Because for me, these two words coming from completely different backgrounds. So how do you combine these two things?
Yeah, so let's see if quantum computing offers a new paradigm for doing calculations. With quantum computers, we can solve problems that are very hard or directly impossible to be solved with conventional computing. Now, quantum computers are also remarkably good at, say, solving optimization problems, also at recognizing very subtle patterns in the data. And these are types of problems that we find in finance. So finance, as such, is it's a science of what happens with money, and it's strongly mathematical. So there are zillions of mathematical problems in finance and in economy. The banks and the financial institutions, they hire lots of mathematicians, of computer scientists, of physicists to actually program and develop methods to say, I don't know, forecast the market or find the optimal investments or calculate risk, of an economy or predict a financial crash and so on. All this is extremely difficult and time costly with the techniques conventional techniques. And this is, of course, why people in finance are interested in quantum computing. Anything that has to do with numbers in finance, all the programs that people in quantitative finance are doing and so on, all these methods can be improved in some way or another using quantum.
Yeah, so what you're saying is that you take problem in finances, put it, let's say, in mathematical equation, and then quantum computers help you to solve these mathematical equations, right?
Exactly. So, for instance, if you want to do, you want to optimize a portfolio of investments on different assets because you want to maximize the return of your pension plan the day you retire. All right. So, at the end of the day, you can put these on mathematical equations, and you have a very complicated equation that you have to maximize, which is the return. All right. And this depends on many, many variables that are very much correlated with each other. And it's a very difficult mathematical problem to find the optimal investment that you should be doing, say, every day or every month in order to maximize the return. The reason why this is very difficult is because, this is one of those problems that are among the hardest mathematical problems. The solutions that are offered by conventional computers are suboptimal. We know that. And we know that quantum computers are precisely very good at solving this type of problems. You have many variables, they are very correlated with each other, and say you need to for instance, in this case, to maximize the return. Okay, so this is something that the quantum computer could do more efficiently.
Yeah, and if you look, let's say, at the world of classical computers still, so what's the state of the art with classical computers and why do we need quantum? Because it's completely different approach, or how quantum compete with classical in this field?
Yeah, so classical computers are, of course, very useful, but they are limited. So there are problems that they can simply not solve. For the case of, it depends on the particular type of problems that you want to do in finance. But for instance, if it's about evaluating a portfolio, the thing that I was mentioning before, So the solutions that classical computers are offering, we know that they are suboptimal, and with quantum computers, we could obtain much better results. But quantum computers could do many other things. Say, for instance, there are many applications of in finance that are based on stochastic algorithms. There is something called Monte Carlo methods that are used very widely in finance, and they have a particular running time. And we know that with quantum computers, once we have them, we have prototypes more developed, we will be able to perform those calculations also faster. Okay. Also, when it comes to artificial intelligence, nowadays, current artificial intelligence is very good, but we know it is not perfect. It's not possible to detect, for instance, all the cases of fraud, or detect all possible anomalies in a data, because there are some limitations, and we know that quantum computers are more they are more efficient and they are more precise at the time of detecting anomalies. Okay. Now, quantum computers are still a little bit on their infancy. Quantum processors are small, they are noisy, and so on. And it looks like we are mainly doing toy models. But this is changing very, very quickly. So in the next, I will say that in the next few years, we are going to see a dramatic change along this direction. And we're already starting to be able to solve problems in finance with real data and not just toy models using quantum computers.
Yeah. And let's say when we're talking about quantum speed up, so what exactly, could you give us some numbers if you compare classical to quantum? How bad is quantum computers?
Yeah, I mean, the typical example is the example of factorization. So this is a paradigmatic problem. Okay, so imagine that I give you a number, and you say 15, and you have to find the prime decomposition. So 15 is equal to 3 times 5. This is very easy, no? If I give you the factors, it's very easy to multiply. But if I give you the original number and I tell you, well, what are the factors? This is a problem that is known to be very difficult for our current machines. I mean, not for 15. For 15 is very easy. But if I give you a number with 700 digits, okay, or 620 or something like that, then the complexity of the problem grows up very quickly, exponentially fast. This problem is important not just for mathematics; it's also important for cryptography, because our current, crypto systems are based on this type of problems. For instance, RSA and so on, they are based on the fact that this problem of factorization is very hard for classical computers. And well, to give you some numbers, if you want to solve this problem for a 617-digit number, such as the standard that is being used nowadays in some cryptographic protocols, with the best classical algorithm that we have, I think it will take you of the order of 320 trillion years, all right? Which is not very practical. And with a quantum computer, it will take you a few hours, all right? So that's just to give you an example of why quantum is different, okay? I will say this is the most dramatic example. In this case, you have an exponential speed up.
Yeah. And you already mentioned, of course, the next sort of natural question will be about practicality of quantum computers, because right now we know that quantum computers are relatively weak, right? On the small, not so many qubits, they're kind of dirty, very noisy. So now the question is, when we're talking about quite complicated problems, let's say factorization of big numbers, how we can recombine it with quite weak computers which we have right now?
Yeah, well, the point is that for some problems, not all problems that you have to solve on a quantum computer have the same degree of complexity. So for some problems, such as factorization, you need very large quantum computers with many qubits that are error corrected, and they are not noisy, and they work very well. Even though this is being reevaluated every day as we speak. But for some other applications, surprisingly, you don't need so many qubits. And with a small, noisy, and intermediate scale quantum processors, such as the ones that we are having nowadays, you can already start doing serious things. So there are two important applications there that I think that they are going to come sooner than later. One is quantum optimization, and the second one is quantum machine learning. So everything that has to do with quantum artificial intelligence. These two types of algorithms, they don't need many logical qubits to run. Okay, say the quantum machine learning algorithms, they can run on a small noisy processors. They don't need too many qubits because it's not so much about the speed up of the calculation, but rather about the precision and the ability to detect patterns in the data. And this you can already do with few qubits. And since these algorithms are heuristic, they are very robust to noise, actually. And this is one of the first applications, and with higher impact, that is going to be running on quantum computers. All right. Actually, in the prototypes that we have nowadays, we can already start implementing them. Okay. And the other one is quantum optimization. We have already some quantum processors that are very good at optimizing, for instance, D-Wave. There is also the ability to, propose hybrid solution, part classical, part quantum, a little bit the best of both worlds. And this allows to, solve even larger problems. And this is also one of those applications that that is coming sooner. Okay, so we don't need to wait until having a quantum computer with 1 million qubits. We can already start using them right away.
Yeah. And when you're talking about this application, how many qubits you have in mind, just to get a number?
Well, for quantum machine learning, the processors that we have nowadays that are around 50, 70 qubits, this can already be used for non-trivial applications, even with less qubits. Okay. For quantum optimization, well, if you want to use universal quantum computers, such as the ones that are being built by IBM or Google, I think you still need more technological development. If you want to use the type of quantum computer that is being built by D-Wave, which is a different type of computer, they do something called quantum annealing. In this case, you can already start putting relevant problems there. So I think the last processor from D-Wave, they claim to have 5,000 qubits, but these are not standard qubits such as the ones that you will find in other companies. They just do quantum annealing. They are noisy. They have a finite temperature, even though it's very low. But the machine is there and it's extremely fast, and you can already start using that for serious problems.
Yeah, and when you say serious problems, like how close is to really practical application, let's say in finances, because it might be already a supremacy compared to classical, but are we getting close to real practical problems?
Yeah, absolutely. Yeah. So, for instance, for finance again. So, for this particular application of portfolio optimization, together with a couple of banks here in Spain, we did a portfolio optimization for 52 and 58 assets. And for different periods of time. In one case, it was for 1 year, in the other for 8 years. So this is real life data. Yeah, and these are problems that are of considerable size already, of the type of problems and optimizations that the quants working at the banks are actually facing. Yeah.
And let's say classical computers can address the same problems, or it's really just quantum shows that it's better, faster, something like that?
In this case, quantum is better. Yeah. Classical computers can also address this problem, but we saw that the solution they were providing was not optimal.
Yeah, and now you're really talking about practical applications. So what do you see the feedback from, let's say, financial community, let's say from banks? Are they happy? Do they want to put more, let's say, money, efforts, energy into this and developing these algorithms?
Yeah, well, it depends on the bank. It depends on the bank. What we are finding is that they, yes, they know about the technology and they are interested on learning about it. They know that this is going to come and it's going to affect them. It's a type of technology that they need to be ready for, and they are training their own internal teams already on quantum computing. So I know of many banks that are already testing the technology, either with us in Multiverse or with other people, and they want to have a taste of what is to come. Yeah.
And so the main benefits here, let's say, or let's say the main difficulty maybe is to use is to develop an algorithm, or it's really in the hard way. When we're talking about, let's say, bottlenecks, what's the main problem here? Is it to develop a nice algorithm or to improve the hardware?
Well, I think the hardware is somehow a bottleneck, of course, but this is unavoidable. So it goes at the speed that it goes, and of course, improvements in the hardware will always be very much welcome. A bottleneck that we are identifying is that it's hard to talk to financial institutions unless you you also know their language. Okay, so if you come from academia, say like me, and you go to a bank and start telling them about Schrodinger's equations or unitary evolutions and so on, they will not understand anything because what they know is about financial derivatives or portfolios, evaluating the risk of whatever. No, so for us it has been instrumental to know how to talk to banks. We have experts in finance. We know really well how it works inside of a bank. What are the specific problems that they have? Okay, and then we have been able to understand their problems and solve them with quantum technologies. Okay, so this is one of the bottlenecks, I think. Being able to identify the correct algorithm for the correct problem. This is something that, even though it has nothing to do with technology, for the quantum startups that are popping out nowadays, this is something that is literally non-trivial. So. Yeah.
So if I understand you correctly, you identify specific problem in finance, and then you try to tailor an algorithm for this specific problem and to match it with the hardware, right?
Yeah, exactly. So it's not about you don't go to a bank and tell them, tell me your problem, and then I will solve it. No, it doesn't work like that. So you have to go to a bank and tell them, look, I'm gonna solve this problem that you have in this way. Okay, that's how it works. And it's very difficult to do that because first of all, you need to understand from their point of view what is their problem, and then how will you solve it using quantum computing. No, so yeah.
Yeah, I see it. It's quite an interesting approach. So pretty much, let's say if you're talking about customers, so your customers will be quants department in banks, let's say, right?
Yeah, exactly. Yeah, for portfolio optimization, yes.
So people, and let's say if people want to use quantum computers, do they have to have a background in quantum physics? So let's say you're going to a bank, right? And now you're talking to people and you're trying to convince to use quantum computers. Do they need to have some background in quantum, at least understand your language?
Yeah, well, I think that the people inside of the banks are training their own teams. So they need to, I mean, the more background on quantum they have, the better. That's true. And always inside of banks, there is some physicist, say, or some mathematician. And these are people that can follow the technology. But more and more, we are talking to actually experts on artificial intelligence who know nothing about quantum, but they know about programming and about coding, about machine learning algorithms. And yeah, so these are people that we can also talk to.
Yeah. And you know, when I look at the packages which was developed by IBM, Google, it seems like more like a toy model, playing it. You don't need to understand even physics. Sometimes I feel, maybe I'm completely mistaken, but sometimes it seems to me like you're just playing with toy models, placing these quantum gates. And sometimes I feel you don't even need to know physics, like just some basic understanding of programming. So do you have this feeling?
I agree. Yeah, I think it's very important to make it very simple for the people to program. So, you know, this is just a new computational model. And from the point of view of somebody doing, say, computer science, they don't need to know quantum mechanics. They just need to know, well, look, these are the rules. And we stick to the rules, okay? So there are vectors, there are Hilbert spaces, operations are like this, and that's it, okay? And with this, that's all they need to know, yeah.
Yeah, and then let's say if you want to develop an algorithm, you have to do something really smart, right? Because you don't have so many qubits and you have to package all your problem into less amount of quantum gates, right?
Yeah, exactly. Yeah.
Yeah, okay. Let me maybe go to a bit a different thread. You mentioned already quantum annealers, and I think the development with quantum annealers is better with the universal quantum computer. So could you say a little bit what's the future or what's the goals and what we can do with quantum annealers?
Yeah, so quantum annealers are quantum processors that are built for one task only. They are built for optimizing cost functions. They solve something called a quadratic unconstrained binary optimization problem. It's a very particular type of optimization problem, but it's sufficiently general in order to be applied to many different tasks. Okay. Now, since quantum annealers are built only for one purpose, I think that they are easier to build than just a universal quantum computer. Of course, we want to have universal quantum computers to run any possible quantum algorithms. But on the other hand, I have the feeling, I think it's also correct, that essentially almost any problem can be mapped to an optimization problem. So at the end of the day, you can also use quantum annealers to solve whatever problem you have. No? Now, there has been a lot of development of quantum annealers because it was the first quantum computing approach that was taken seriously commercially. This was because of D-Wave. And of course, at the beginning, they were criticized a lot by the academic community, of which I am also part of. Okay, but nowadays they are more open, and I think that the progress that they are doing is very impressive, and they are also, implementing improvements on their machine, also combining it with new techniques to make hybrid algorithms to make it more powerful. So yeah. From my perspective, I think quantum annealing is an approach that is very close to physics, more than to computer science. And physicists tend to like a lot quantum annealing because it's about, we have lots of problems of minimizing functions in physics, and this is why we like it a lot. I have the feeling that universal quantum computers are more appealing to people in computer science, no? Simply because of the way they work.
Yeah, and can we address, let's say, practical problems with quantum annealers and to show that they're already better than classical computers?
That's a good question. Yeah, well, actually, what we did with portfolio optimization, as far as we know, was better than what it was being done inside of the bank. And I have the feeling that there are some works with quantum annealing where they have been using them to study quantum phases of matter, actually topological phases. And as far as I understand, those are very complicated calculations if you want to do them classically, and with a quantum annealer, they were able to study them. Yeah.
Yeah. And maybe another still subject is quantum-inspired algorithms, right? It's kind of close. So could you talk a little bit what's quantum-inspired and how we can use this approach?
So quantum-inspired algorithms are classical algorithms. They don't run on quantum hardware. They run on your laptop or on an HPC or a GPU. But they are called quantum-inspired because they have been born precisely because of how we have understood how a quantum computer works. Okay. So there are different approaches here. One is, for instance, tensor network methods, which come from, they have an old story in condensed matter physics and quantum information. We've been using them to simulate strongly correlated quantum many-body systems. And nowadays, we can also use them. We are also using them for solving optimization problems in industry and also developing new machine learning algorithms that are more efficient. Okay. There is Fujitsu also has something called digital annealing. Okay, which is an emulator at the classical level of a quantum annealer. Instead of having say a quantum processor, we have a classical processor that is trying to mimic what the quantum is doing, but at the level of hardware. Okay. Microsoft also has a quantum-inspired optimization toolbox, which is a classic, it's a very advanced classical algorithm for optimization as well. So yeah, these are methods that they are not quantum. They are classical, but they are inspired by quantum. And in many cases, they work better than the state of the art. And
so we can say that sometimes quantum-inspired algorithm could perform better than, let's say, any other classical algorithm.
Yeah, absolutely. Yeah, and this has actually been proven in many situations already. Yeah.
Yeah, and let's say, when you're talking about quantum-inspired algorithm, just quantum algorithms, can you borrow some algorithms, let's say, from different fields, let's say solid-state physics, I don't know, space, studying something, black hole matter, whatever. So is it possible?
Yeah, absolutely. So as I told you, well, the example of tensor networks is a good example. They have been developed in condensed matter physics and statistical mechanics before that, and then in quantum information theory, and now they are jumping to machine learning. And turns out that there is a paper by Google out there that shows that they are better at anomaly detection than deep learning, okay, which is the best you can do. So yeah, absolutely. And even, not just in quantum inspired algorithms, but also in the field of machine learning itself, people are using algorithms that they do, say, that they use in physics, for instance, in particle physics, let's say, to filter data, also to, for finding other applications, say, in finance or in industry. Yeah.
And actually, you mentioned quantum machine learning, and when I hear this phrase, for me, it seems like it's really far away because it's quite complicated algorithms. I mean, even classical machine learning is quite a relatively new field. But when we're talking about quantum machine learning, it seems to me quite new and complicated. So is it possible to address it somehow with quantum computers already?
Yeah, absolutely. It's actually one of the fields that is coming sooner. So it sounds very science fiction, but it's not so science fiction. Actually, I would say is the quantum machine learning algorithms are a type of algorithms that are built, are kind of tailored to these processors that we have nowadays that are small and noisy. Okay, so you can understand them in many ways. There are different families of quantum machine learning algorithms, all right? But you could think of generalizations, let's say, of neural networks to quantum circuits where you have some variational parameters and you have to optimize those to minimize some cost function or some class, the error on some classification or something like that. So yeah, these are algorithms that even though they sound a bit like science fiction, they are actually the type of algorithms that is better adapted to the type of hardware that we have nowadays.
Yeah, and maybe it's quite naive question, but how it goes? You're looking at the classical machine learning and then you adapt it to just making a quantum twist, or it's completely new algorithms not related to classical?
It actually goes in both ways. So there are different trends in quantum machine learning. One way is to pick up the classical algorithm, say neural networks, and say, okay, let's try to quantize this, whatever it means. No? The other option is to try to build an entire algorithm from scratch that has no classical analog, and that you could try to argue that, look, we have a quantum computer that is learning something. Okay, so yeah, this also exists.
Yeah. And let me maybe go to a different subject. You mentioned that you are a co-founder of the company Multiverse Computing. So could you talk a little bit about the company, what's the goals, what's the vision?
Yeah, so Multiverse Computing is a company that we built a couple of years ago. We are the world leaders of quantum computing software for finance. We have headquarters here in Spain. We have another office in Toronto. We are opening soon in Paris and also Munich. Right now we are 16 people on the whole, and we closed pre-seed funding round. We are going to be closing another funding round during this year, and we were expecting to grow, okay, to double numbers during the year. And yeah, so it started a little bit like like a group of friends, let's say, that we had this. There was this question around of whether we could apply quantum computing to finance, and then we just joined and started thinking about that. Realized that yes, it could be done. We wrote a paper about that. It was very successful, and then the banks started calling us, and then we decided, okay, we need to make a company here. That's how it started.
Yeah, very nice story. And what's the background of people working in this company? It's more like physical background or something else?
Yeah, so there is a bit of everything. So among the founders, there are 2 physicists. One of them is me, and then 2 business people. One of them actually also has a finance background. And then the technical people, they are mostly physicists, okay, and also machine learning engineers, programmers. It depends on the role, okay? So there is a good bunch of physicists, of course. But we also need, computer coders, okay? Because we need to develop very good code. And then, of course, at some point, we also need business and administrative people. But the technical, I would say the most important bunch of people here are physicists.
Yeah, and how do you see your potential clients and what type of problems you would like to address with this company?
Well, clients are anybody in finance that is using a computer, as simple as that. So, people inside the banks that are using computers to do calculations, to make predictions, to optimize asset funds, compute the risk of an investment fund or whatever. All these are our potential clients. Yeah, the people in doing quantitative finance. And also, investment funds, central banks, also financial departments of large institutions also. Yeah.
And so your goal is to show that quantum computers can do better and outperform classical, or you're trying to combine classical with quantum? So what's your approach?
Both of them. So we offer quantum and quantum-inspired solutions. Yeah. And we also offer hybrid algorithms between quantum and classical, because that's the state of the art. Okay, and yeah, that's what we do.
And when you show, let's say, that the quantum is better, how you can prove it? Because I might suspect that people in finances that may say, oh, you just show something, but it's not necessarily true that quantum is better. That might be quite suspicious, no?
Well, we have some numbers, and then we ask them, "Are you able to beat this?" And then they tell us no, and then that's it.
Okay.
Okay.
Yeah, fair enough. And maybe I would like to ask you about your another activity, which is entanglement partners. So could you talk a little bit about this activity?
Yeah, so I'm involved in another company, as you said. This is Entanglement Partners. This one is older than Multiverse Computing. It's a consultancy company on quantum technologies. It's based in Barcelona. It has a focus more on cybersecurity. Okay, and yeah, it's more. I have the role there more of an assessor, say. Yeah.
So, and you say quantum security, so it's more like to prevent, as you said, RS-32 breaking, let's sort of prevent of, let's say, frauds with money or cracking the, I don't know, Gmails, whatever emails you have.
Yeah, exactly. Cybersecurity risk, yeah, and also quantum cryptography.
Yeah, I see.
But yeah, exactly. But it's more the role of an assessor, let's say. So it's.
I see. And you still have another activity which I would like to ask you is Quantum World Association. So could you talk a bit about that?
Yeah, actually, this is interesting. So this Quantum World Association is a non-profit organization that was born before Multiverse Computing. And at the beginning, in this non-profit organization, there were different working groups, and one of them was called Quantum for Quants for Quantitative Finance. And this is exactly the group of people from which Multiverse Computing was born. Okay, so it's a non-profit organization. I was involved in this, and we had this working group on say, okay, let's see if we can apply quantum computing to finance. The answer was positive, and then the people inside of this group that that was carrying the thing forward, we decided to build Multiverse Computing.
Yeah, I see. And I think we're coming to the close of our discussion. I would like to ask you a couple of last questions. And my first question will be about, let's say, positive news in quantum field and the media. So what do you think about very positive news about quantum? Do you think that they're real? And what's your filter when you're reading news in quantum field?
Well, I think, of course, there is some hype,
yeah.
Okay, on the community. I think one needs to be careful, all right? But on the other hand, one needs to be optimistic and stay positive. So not everything that is said is not true. Let's put it like that. Okay. So yeah, of course, there is a lot of hype. One needs to be conservative, especially people from academia. They are very conservative, and that's very good because that's how they need to be. On the other hand, it's also true that there is a lot of very quick, very fast development in recent years. Okay, and this is a reason to be very optimistic. So, for instance, every time that there has been a problem for some reason or another, through investment of neurons from people and also capital, we've been able to overcome it, and that's what has happened actually with the progress in the recent years. Look, when I did my PhD in 2006, I was saying that I will never see a quantum computer, that probably maybe we could see it in 200 years. And now we have already a 50 qubit working quantum computer. And this is the last thing I could think about, maybe 3 years ago. So I always tend to say that we cannot imagine the future, but it always comes faster than what you expect. And that's also my feeling. I think there is a lot of hype. It's true. But there is also very positive signals coming around. For instance, there are people that are already thinking about how to scale up quantum computers by building them in racks and connecting them through fiber optics and so on. These are things that, sooner or later they are gonna hit the industry. And I don't know. I think it's a reason to be. There are reasons to be optimistic.
Yeah, and I guess my last question will be about timestamps. What do you think the milestones are coming in the future, and what's the time schedule for that? What type of problems we can address?
I don't know. I mean, our time scales. Yeah.
It is a speculation, of course, but maybe we can speculate a little bit.
So in 5-7 years, I think we are gonna have quantum computing. I mean, quantum supremacy is gonna be for sure a fact, and we are going to have quantum computers that will already be deployed in industry into actual industrial applications as a common story. In 5 to 7 years, I have the feeling that the field is going to explode exponentially fast in this period, and there are going to be many quantum startups coming up, especially in software for software applications. And I think that there is also going to be a lot of movement in the field.
Yeah, I think it's a positive attitude, and let's see what future prepares for us, and let's see how it goes. Okay, I think thank you for your time and efforts for joining me today.
Thank you.